Time for a little more review. We are now going to talk just for a short time about vectors and coordinate systems. Again, nothing difficult here. You already know this. You maybe don't have the labels, but you already know this from everyday life. So we're going to have to go through this because this is going to apply to our space-time discussion later on. First thing we want to talk about quickly is a vector. A vector is simply a mathematical object that has both a magnitude and a direction. So for example, an example of a vector would be your car driving down the road. You could be going north at 60 miles an hour. That's a magnitude of 60 miles an hour and a direction of north. Very simple. That is represented by this arrow here and this line. The length of the line is represents 60 miles an hour. The arrow just represents the direction. Pretty straightforward. There are also things you're familiar with called scalars. Scalars are things like temperature. The temperature of this room is 65 degrees. Perhaps my weight, which is sitting at about 250 pounds right now. I don't know if that's a scalar or not, though, because it seems to be going up. So maybe it does have a direction. In any case, humor aside, the vector has a magnitude and a direction. A scalar quantity, which we're not going to have to worry about, is just something that has one value, like the temperature in the room. Over here, we have a coordinate system. I don't think that's going to take much explanation at all. That's a map. Everybody's GPS system, we've all seen maps. We've all used maps. We got north and east. What we want to do is we want to lay our vector on top of our coordinate system and see what we can get out of that. So let's do that now. And now that we have our vector laying on top of our coordinate system, down here meeting at the origin, our vector can rotate like this. And no matter which direction it's pointed, it's always the same length, which means it's always representing a speed of 60 miles an hour. Anywhere along this red curve is going to be 60 miles an hour. So very simple. In this case, it's pointed at a 45-degree angle. So let's see what we can do about that, or what we can do with that. I'm adding what they call vector components, another really fancy term for just means it's a couple lines to show you how that vector projects on each axis. It's going to, if you're going northeast, like this shows a very nice northeast direction, exactly 45-degree angle. So that works out real good. We're headed northeast. Simple. So that means we're sacrificing some of how fast we're going north in order to go somewhat east. In this particular case, we're going as much east as we are north because it's exactly a 45-degree angle. And so your car is going 60 miles an hour. Now, when you want to look at this distance here, we're going to see that the car is going 42 miles an hour in the north direction, and the car is going 42 miles an hour in the east direction. And that's going to yield us this vector that goes 60 miles an hour. Represents 60 miles an hour. I'll explain that in a second. The way to think of these projections here is that, or these vector components, is think of a light shining coming in through here. When it hits the vector, it casts a shadow of the vector over here. Where that shadow hits over here, this distance is going to be the shadow on the north axis. And then the light could also be coming from the top down, and it's going to hit the vector, and that casts a shadow down here of this. Now, it so happens that if you do the mathematics, it turns out that you find that if you're going 60 miles an hour northeast, you're going 42 miles an hour north, and you're going about 42 miles an hour east. And if you combine those two, you get 60 miles an hour. I'm going to make one little deviation here into a little bit of math, just so we're clear on this, that you don't, if you say, well, if you add 42 and 42, you get 84. So this must be 84 miles an hour. No, that's not true. That's not how it works. What you'll notice is that this is a right triangle, okay? So we apply what we learned in high school was the Pythagorean Theorem. So if we take 42 and square it, and we take this 42 and square it, and then we add those two together, and then take the square root, we are going to get very close to 60 miles an hour. That's how you have to add these things. You can't just add the numbers together. It won't work. You don't actually have to know that to understand the relativity part of this. Okay, so I'm interrupting a regular video for a mathematics alert. And so in our mathematics alert, I'm going to talk very briefly about the Pythagorean theorem. Let's do a quick review of that because we are talking about it and we are using it. So just to quickly explain and remind everybody what it was or is, it's a right triangle, side A, B, and C. And if we remember from our mathematics, probably junior high school mathematics, A squared plus B squared equals C squared. That's it. A squared plus B squared equals C squared. That's the hypotenuse. So let's try a quick example here just to see how this works. And if we go here, we can assign some values to our sides. We'll make this one 48 miles an hour, make that 36 miles an hour. So remembering that A squared plus B squared equals C squared, we can see that 48 squared plus 36 squared, our two sides, equal 3,600. If we just simply take the square root of that 3,600, we get 60, and that's our 60 miles an hour. And that is all there is to it. That's the Pythagorean theorem. So let's get back to our regular business here. Let's take another look at an example here that might help clear it up more. Here we have a 65-degree angle. This time we're going very much north and not very much east at all. And so in this particular case, with our car still going 60 miles an hour, but now we're going mostly north. So we're going north at 54.4 miles an hour. We're going east at 25.4 miles an hour. Those are the two components of our vector. And when you use, again, the Pythagorean theorem, if you square this, and then you square this, and you add the two together and take the square root, you'll get about 60 miles an hour. So the math works. Again, you don't have to know it. Just be aware of it, that there's some math behind this that works out correctly. But what you're doing is you're trading, instead of just going straight north, you're trading some of how fast you're going north so that you can go a little bit east because the town you want to get to is up here somewhere. Okay, so you're going to have to make a trade-off. You can't just go north or you can't just go east. You go somewhere in between. And this just tells you how fast you're going east and how fast you're going north. Let's look at just one more. There we have 59.8 miles an hour headed east, but 5.2 miles an hour headed north. This vector now is laying at only about a 5-degree angle. And so if you get down to a 5-degree angle, you're headed very much east and hardly north at all. But you're still going 5.2 miles an hour in a northerly direction, and you're going 59.8, which is almost the entire 60 miles an hour is headed east. And again, the Pythagorean theorem is what you have to do if you want to be able to calculate that 60. Don't just add these two together. It won't work. So I think that it pretty much concludes what we need to do to review vectors, coordinate systems, and how they interact with each other. Let's just take another look back here. There's our nice 45 degrees. We're headed exactly northeast. We traded some of how fast we're going north so we could go east. And again, we traded some of our northern direction so we could go east, but not very much of it. And then here, we are hardly going north at all. We're going mostly east. Now, if you can get that, if it makes some sense to you, then moving into the space-time and understanding the time dilation is going to be no harder than this. It's not going to be any more difficult than what we're doing right now. So if you get this, you can almost rest assured you're going to get the time dilation part. And that's what we're going to go into next. The next video is going to be the time dilation. And we're going to use this, and we're going to change some of these things, the labels, but the concept is going to stay the same. And you're going to see why it is that if you're going in a spaceship at close to the speed of light, you will age much, much more slowly than me sitting here on the couch. So let's hang on, and we'll see you in the next video.